on to question number 13. Describe how the presence of sulfite ions in aqueous sodium sulfite can be confirmed using aqueous barium nitrate and dilute nitric acid. So you have a sample that you suspect contains sulfite ions and you would like to confirm whether this is actually the case. So you're going to take a sample of the sodium sulfite solution, add 1 cubic centimeters of barium nitrate. Now, if the sample contains sulfite ions, what will happen is that immediately you add the barium nitrate, you are going to end up having a white precipitate. Where does this white precipitate come from? Barium nitrate, which is a soluble salt, reacts with sodium sulfite to form barium sulfite. So barium sulfite is an insoluble salt, and that is the reason why a white precipitate is formed. Now, if you continue with the next step, which is addition of dilute nitric acid, what will happen is that you're going to find that the white precipitate dissolves, okay? Yeah. So the reason why it dissolves is because the barium sulfite will react with nitric acid to form barium nitrate. And remember, all salts of nitrate are soluble. So it's going to form barium nitrate, which is a soluble salt. And that is the reason why you are going to find that the white precipitate dissolves. Sawa? Now, the other observation you're going to note is that there is going to be effervescence. Effervescence simply means, bubbling because of the production of a gas. Where is this gas coming from? It's coming from this reaction. So this reaction will lead to the production of barium nitrate, water, and sulfur 4 oxide. And that is why we are seeing effervescence from the sulfur 4 oxide gas. Part B, acidified potassium dichromate 6. So you're going to add 3 drops of orange acidified potassium dichromate 6 to a second sample of sodium sulfite solution. So the orange acidified potassium dichromate 6 changes to green. This, of course, confirms the presence of the sulfite ions. Question number 14. Use the bond energies in table 5 to calculate the enthalpy change for the combustion of ethene. Okay, so we have ethene reacting with oxygen to form carbon 4 oxide and water. Now, in the table that follows, we are given different bonds and their bond energies. So the bond energy simply means the amount of energy that is required to break apart these particular bonds. So for example, in the first instance, we have a double covalent bond between 2 carbon atoms. If you want to break apart this bond, you are going to need an input of 612 kilojoules of energy. Sawa? So as you can see, each bond has its own specific bond energy. Okay, so what I'm going to do is I'm going to open up the chemical equation so that the bonds become clear to us as such. Now, what I want to mention is this. When it comes to this reaction, what we are seeing here is ethene reacting with oxygen to form carbon 4 oxide and water, but it's actually a reaction that occurs in steps. For example, on this side of the equation where the reactants are, we have ethene and oxygen. What products are formed? Carbon 4 oxide and water. These are 2 completely different products. So that means what happens is that the reactants are broken down to form 3 atoms. And then these atoms then rearrange themselves to form the products that we have. So before we can actually, the reaction can proceed, what happens is that we need to break apart the bonds that are present in ethene and oxygen so that we end up having 3 atoms, carbon, hydrogen, and oxygen, which will then recombine with one another to give us carbon 4 oxide and water. Now let's look at ethene. In ethene, we have a double covalent bond between the 2 carbon atoms. We need to break this, okay? And for us to do so, we need an input of energy, specifically 612, okay? So tunakuja tunaiandika hapa 612. Now we also have bonds between carbon and hydrogen. Each of these bonds requires 496. And how many do we have? 1, 2, 3, 4. We have 4. So 496 multiplied by 4. Haya, tumemalizana with ethene. Let's move on to oxygen. We have 3 molecules of oxygen. In each molecule, you're going to have 1 oxygen atom having a double covalent bond with another oxygen atom as such. So 1 oxygen molecule, another oxygen molecule, and a third oxygen molecule. Now, if we want to break apart this 1 bond, we need 412. But we have 3 molecules of oxygen. So that means we need 412 multiplied by 3. So on this side, on the reactant side, we are done. Now everything that is on this side will have a positive sign. Why will it have a positive sign? Because these are reactions that require an input of energy. They absorb heat energy. And reactions that absorb heat energy are referred to as endothermic reactions. And these are assigned a positive sign. So hapa plus 3,832 kilojoules, right? Now let's tackle the other side, on the reactant side. On the reactant side, we have formation of new compounds. Na tulisema, when new compounds are formed, we have heat energy being released. So that means these reactions on this side, the formation of carbon dioxide and the formation of water are going to be exothermic reactions. So heat energy is going to be released because you are going to have new bonds being formed. Now, in exothermic reactions, we assign a negative sign. Sawa? Okay. Now, let's start with carbon dioxide. That is how carbon dioxide looks like. So, it has double covalent bonds with 2 oxygen atoms. Hapa, over here, we need 743. Over there, 743. Okay? So, that is 1486 for 1 carbon dioxide molecule. So when 1 carbon dioxide molecule is formed, 1486 kilojoules of energy are evolved, are given off. But how many molecules of carbon dioxide are being formed here? 2. So that makes it 1486 multiplied by 2. What about water? In water, we have single covalent bonds between hydrogen and oxygen. So hydrogen and oxygen over there, 463. And over there, another 463. So in 1 molecule of water, when 1 molecule of water is formed, we get 926 kilojoules of heat energy being evolved. But how many molecules of water are being formed? 2. So 2 multiplied by 926. Sum all of these. And remember, we are going to assign these a negative sign. So we get plus 3832 minus 4824. The last step is simply summing up. Kila kitu tu unachanganya. But remember their signs. So when we sum these two, we end up having negative 992 kilojoules per mole, showing us that overall reaction is exothermic because more heat energy is released than is absorbed. Next question. Ethanol can be prepared from glucose according to the following equation. Okay, so we have glucose at 30 degrees Celsius being broken down to form ethanol, which is an alcohol, plus carbon dioxide. Part A. Explain why temperatures more than 30 degrees Celsius are not used. Now, this is an example of anaerobic respiration, where food substances are broken down in the absence of oxygen. Now, this occurs in yeast cells, right? Now, in yeast cells, we have enzymes. And enzymes, as you know, are organic catalysts. They speed up the rate of reactions. So we have specific enzymes in yeast cells that are involved, in breaking down of glucose to form ethanol and carbon dioxide, and in the process, release energy. So if you have temperatures that are above 30 degrees Celsius, what will happen is that the high temperatures will end up denaturing the enzymes. You know, enzymes are made from proteins and they are very sensitive to temperature changes. So if you have high temperatures, they will destroy the enzymes. And if the enzymes are denatured, will the process actually take place? No. The anaerobic respiration will simply stop. So no fermentation. Part B. The concentration of ethanol in the product is about 12%. State how the concentration of ethanol in the product can be increased by carrying out fractional distillation of the crude solution. Part C. State one use of ethanol in hospitals. This is used as an antiseptic. Question number 17. The following steps are followed when carrying out paper chromatography of a dye. Number 1. The solvent is placed in a beaker. A baseline is drawn with a pencil on the paper. There you go. Step number 3. The sample is spotted on the baseline. Number 4. The paper is carefully placed in the beaker with the baseline above the surface of the solvent. Step number 5. The beaker is covered and allowed to stand for some time. Give a reason for the following. Part A. The baseline is drawn with a pencil. Okay. Now, in most cases, the tips of pencils are made from graphite. And graphite is not soluble in the solvent. You know, it does not dissolve in the solvent, which is very, very good. Because if it were to dissolve in the solvent, it will interfere with the separation process. So pencils are used because they have graphite and which does not dissolve in the solvent. Part B. The paper is carefully placed in the beaker with the baseline above the surface of the solvent. Now, we don't want the baseline coming into contact with the solvent because if the baseline were to come into contact with the solvent, what will happen is that the sample that was placed in the baseline is going to dissolve in the solvent. So instead of it spreading upwards, it's just going to, dissolve in the solvent and spread downwards into the solvent. We don't want that. We want it to move upwards. And that is the reason why when the paper is placed, you ensure that it's above the solvent. Part C. The beaker is covered. Now, the solvent is highly volatile. Actually, most solvents are. So what do we mean by volatile? That is, they can easily evaporate at room temperature. So it's covered to prevent the solvent from evaporating because most solvents are volatile. Okay, moving on to our next question. 6.12 grams of hydrogen peroxide were dissolved in 100 cubic centimeters of water. The peroxide was allowed to decompose in the presence of a catalyst and oxygen gas produced was collected. Okay, so we have hydrogen peroxide decomposing, okay, to form water and oxygen. Part A. Name a suitable catalyst for the reaction. So the catalyst that is used is manganese or oxide. Part B, Roman 1. Calculate the number of moles of hydrogen peroxide in the solution. So we are going to use this formula. Number of moles is given by mass over the molar mass. The mass of hydrogen peroxide is 6.12. What is the molar mass? We can easily get that. So we are going to take the RAMs of hydrogen and oxygen, just sum them together. So we have two hydrogen atoms. Each has RAM of 1 by 2. Oxygen, of course, is 16 and they are 2. That gives us 34. So 6.12 divided by 34 gives us the number of moles of hydrogen peroxide as 0.18. Roman number 2. Calculate the volume of oxygen produced. Okay, so we are being told that the volume of 1 mole of a gas is 24,000 cubic centimeters. So this simply means that at room temperature, the volume of 1 mole of any gas occupies 24,000 cubic centimeters. Now, what do we have regarding oxygen? Do we know, the mass, the moles? No. But we can use the mole ratio to get the number of moles of oxygen. If we look at our balanced chemical equation, we have 2 moles of hydrogen peroxide decomposing to form 2 moles of water and 1 mole of oxygen. Now, according to the information provided, the actual number of moles of hydrogen peroxide were 0.18. So if 0.18 is equivalent to 2, what about 1? So 0.18 divided by 2 will give us the number of moles of oxygen as 0.09. Now we have the number of moles of oxygen. The only thing that we are left to do is simply refer to this information. 1 mole of a gas, any gas, occupies a volume of 24,000 cubic centimeters. What about 0.09 moles of oxygen? So to now cross multiply, and we end up having the volume of oxygen as 2160 cubic centimeters. On to our next question. The setup in figure 2 is used to prepare carbon 2 oxide from ethane dioic acid. The equation for the reaction is as such. So ethane dioic acid, when heated, decomposes to form carbon 2 oxide, carbon 4 oxide, and of course, water. So identify X and Y and give the role of each. So X, that is concentrated sulfuric 6 acid, it's used as a dehydrating agent, to absorb moisture. Roman 2, Y. Y is concentrated sodium hydroxide solution. This, of course, is used to absorb carbon 4 oxide, because at the end of it, our role is to collect carbon 2 oxide and not carbon 4 oxide. So we need to find a way to remove the carbon 4 oxide. And that is where the sodium hydroxide solution comes in. It absorbs carbon 4 oxide, allowing us to collect the carbon 2 oxide. Part B, state a property of the gas that allows it to be collected as such. So what is the method of collection? Over water, specifically over warm water. Now, carbon 2 oxide is insoluble in warm water, and that is the reason why it's collected as such. Moving on to our next question. 2 grams of hydrogen gas was reacted with 2 grams of oxygen gas to form water. Calculate the mass of the water produced. Now, before we calculate the mass of water, we need to have a balanced chemical equation. This is going to act as our guide. So there we have it. So according to this equation, 2 moles of hydrogen gas will react with 1 mole of oxygen gas to form 2 moles of water. Now, does it mean that in every reaction, you are going to have 2 moles of hydrogen reacting with 1 mole of oxygen? Of course not. This simply, acts as a guide by letting you know that in whatever reaction these two participate in, the number of moles of hydrogen gas will always be double those of oxygen, okay? Now, in this case, do we know the number of moles, the actual number of moles that are present in hydrogen gas? No, but we can easily find out. So we are going to use this formula, mass over the molar mass. The mass of hydrogen is 2, the molar mass of hydrogen gas is also 2. Remember, hydrogen is diatomic as such. So each hydrogen atom has the RAM of 1, 1 by 2 gives us 2. So we divide the mass over the molar mass and we get the number of moles of hydrogen gas as 1. What about the moles of oxygen? Moles of oxygen, again, we are going to take the mass, which is also 2. Divide by the molar mass, which in this case is 32. Why? Each oxygen atom has 16 multiplied by 2 gives us 32. So when we divide, the mass by the molar mass, we get the number of moles of oxygen gas as 0.0625. Now guys, I want you to look at these two, compare these two. Moles of hydrogen is 1. The moles of oxygen, 0.0625. That definitely shows you that the hydrogen gas was in excess. Okay? So if we look at the information that we have over here, the mole ratio, right? The number of moles of water that were produced were 2. So if we go with the information of oxygen, that the number of moles, yani 1 mole is equivalent to 0.0625, what about 2 moles? 2 moles multiplied by that will give us the number of moles of water produced as 0.125. Okay? Sawa? We are just equating the mole ratios. So the number of moles of water are 0.125. So for us to get the mass of water, we are going to take the moles multiplied by the molar mass of water, which is 18. Sawa? 2 and 16. Multiply these two and we get the mass of water produced as 2.25 grams. Part B, the mass of the unreacted gas. So essentially the question is simply asking us for the mass of the excess hydrogen gas. Now, how many, moles of hydrogen gas did we have initially present in the 2 grams? We had 1 mole. But according to the information that we have, how many moles of hydrogen gas actually reacted? 0.125. Only 0.125. So that means the rest were excess. So if 0.125 moles were the ones that reacted, what is the mass of the hydrogen gas that reacted? We are going to take the moles multiplied by the mass. This is going to give us 0.25 grams. This is the mass of hydrogen gas that reacted with oxygen. What is the total mass that we had initially? 2 grams. What is the mass of hydrogen that reacted? 0.25. So the difference between these two will give us the mass of hydrogen that didn't react, that remained unreacted, that was in excess. So this is going to be 1.75 grams. Question number 22. Activation energy is the energy required to initiate a reaction. Part A. Explain why reactions differ in their activation energy. Okay, so we have different types of bonds that are present, and each bond requires a specific amount of energy in order to be broken down. And that is simply the answer. Bond energies of reacting particles are different. Part B. Figure 3 shows energy against progress of reaction carried out in the presence of a catalyst. Okay, so what happens is that the catalyst usually lowers the activation energy. We talk about catalysts speeding up the rate of a reaction, but how they do so is by lowering the activation energy. So if less energy is required, that means that the reaction can occur very quickly. So sketch on the same axis the curve obtained if the reaction was carried out without a catalyst. Give a reason, okay? So if we don't have a catalyst, the reaction will still occur, but the activation energy required would be higher because we don't have a catalyst. What is our reason? Catalysts lower activation energy by providing an alternative pathway for the reaction. So without a catalyst, more activation energy is needed. Next question, part A. Complete table 6 by filling the missing information for phosphorus and iron. So we have, okay, 3 particles, phosphorus, iron, and O, number of electrons, number of protons, and number of neutrons. So let's start with the first one, that is the phosphorus ion. So over here we have the atomic number that refers to the number of protons. Above is the mass number, that is the sum of the number of protons plus neutrons. So how many protons do we have here? We have 15. Okay. How many neutrons? That is easily obtained. Just find the difference between the mass number and the atomic number. So that will give us the number of neutrons as 16. Okay, so 16 plus 15 ndo tunapata nini? 31. Now for the number of electrons, this is a bit tricky. Okay, there is something here that you have to remember. In an atom, the number of protons is always equal to the number of electrons. But that is in an atom. Do we have an atom here? No. Is the atom in the room with us? It's not. This is an ion. And how do I know that this is an ion? It has a charge. It's negatively charged. Negatively charged ions are those that have gained electrons. How many electrons has this gained? 3 electrons. So initially, the number was that equal to protons, okay? 15. We had 15 electrons in the atom. But when it gained electrons to form an ion, the number of electrons increased by 3, from 15 to 18. And that is the reason why it has a negative charge of 3. Okay, let's move on to the next one, the ion. Get it? The ion. So in the case of the ion, we are being told that the number of neutrons are 30. So the mass number is 56. So we are going to take 56 minus the number of neutrons, which is 30, to give us the number of protons, which is 26. Mass number, remember, the protons and neutrons. Okay, so if you have one of these and you have the mass number, you are simply going to subtract unapata the other. What about the number of electrons? Now let's pause there. In the ion atom, what were the number of electrons? Same as protons, and which were 26. But this is an ion. It's a positively charged ion, showing us that it has lost electrons. How many electrons did it lose? 2. So the number goes down from 26 to 24. And that is why it has a positive charge of 2, because it has lost 2 electrons. Okay, part B. Determine the value of X, Y, and N in the following. So if we look at the element and the information that we have here, so X, okay, let's look at the table. X is our mass number, Y is our atomic number, and N is our charge. So let's start with Y. Y is the atomic number. These are the number of protons, and they are 8. What about the mass number? We are going to take the number of protons, add them to the number of neutrons, which will give us 17 as our mass number. What about N? This is our charge. How are we going to determine the charge? By looking at the number of electrons. So the number of electrons are 10. Look at the number of protons, 8. So that means that the atom of O gained 2 electrons in order, for the number to increase to 10. So if you gain an electron, you end up having a negative charge. Now the number of electrons gained will determine your charge. So it will have a negative charge of 2. Okay, moving on to our next question. The flow chart in figure 4 shows some reactions. Part A, name compound K. K, where art thou? So we have iron reacting with chlorine gas to form iron 3 chloride. Okay. Part B, give the formula of solid L. Okay. So iron 2 chloride will react with sodium hydroxide to form solid L. Now solid L is going to be iron 2 hydroxide. Iron 2 chloride will react with sodium hydroxide to form sodium chloride and iron 2 hydroxide. Now iron 2 hydroxide is an insoluble salt, and that is why it's referred to as a solid. So iron 2 hydroxide. Part C, write the ionic equation for the reaction of step 3. Okay. Next question. Starting and sustaining a fire requires 3 ingredients. Complete the fire triangle in figure 5 by filling in the missing ingredients. Okay, so if you want to start a fire and sustain it, ensure it continues burning, you need fuel, you need oxygen, and you need a source of heat to start it off. Okay, cute question. Our last question. Helium is used in weather balloons. A balloon was filled with 100 grams of helium at 25 degrees Celsius and 1 atmosphere pressure. Determine the volume of the balloon at 25 degrees Celsius and 1 atmosphere pressure. Okay, now we want to find the volume of the balloon. We are going to use this information over here. So the first one is the RAM of helium. The second one is something that we've already gone through, that the volume of 1 mole of a gas at RTP is 24,000 cubic centimeters, which is equal to 24 decimeter cubed. Now we already know the volume of 1 mole of helium gas will occupy this. But do we know the moles of the helium that are present in 100 grams? No, we don't, and that is what we need to find out. So moles are given by mass over the molar mass. 100 over the molar mass, which is 4, gives us 25 moles. So we have 25 moles of helium present in 100 grams. So these are the number of moles. We want to know the volume. So if 1 mole occupies 24 decimeter cubed, what about 25 moles? So cross multiply and we end up having 600 decimeter cubed. Part B. The volume at 10 degrees Celsius and 0.85 atmosphere pressure. So this is where we're going to use this. P1 V1 over T1 equals to P2 V2 over T2. What is our P1? Our P1 is 1 atmosphere pressure. Our V1 is 600 decimeter cubed. You know what we just calculated. Our T1 is 25. But we are going to convert it to Kelvin. So 25 plus 273 gives us 298. Okay. What is our P2? That is 0.85. What is our V2? That is what we are looking for. What is our T2? Our T2 is, 10 degrees Celsius. Okay, so 10 plus 273 gives us 283 Kelvin. So if we make V2 the subject of our formula, we end up having 670.35 decimeter cubed as our volume. And there you have it, folks. Everything you need to crash Chemistry Paper 1 of the KCSE 2024 exams. If you found this video helpful, don't forget to like, share, and subscribe for more exam prep. Until next time, keep studying smart and stay focused.